So now that we've been working with radicals, we can start talking about solving radical equations or equations that have roots in them. Before we do that, I want to talk about just, again, the principles of solving. So this is something this is day one algebra, you're used to solving this. Let me try to get my camera to zoom in, focus in here. So if I ask you to solve this equation, x plus 3 equals 7, and you're doing those algebraic processes that you learned. So you would have learned, well, if I'm wanting to solve a linear equation, I can isolate the variable x by eliminating this plus 3. And so to get rid of this plus 3, we subtract 3 from both sides. And when we subtract 3, the 3 minus 3 is 0. So on the left-hand side, we simply have x, and that x is equal to 4. When we do this subtraction of 3, we're using the addition property of equality. And the addition property of equality says that if we subtract the same value from both sides, then what we end up with is an equivalent equation. Two equations are considered equivalent to each other if they have the same solution set. So most of you and most of us in general are taught that once you get to here that this is your solution. But in actuality, what you really have is another equation, and that solution of that equation is obvious, because for x to equal 4, then x would have to equal 4. So what really we have is another equation, and the solution to that equation is 4. Okay? Both this equation and this equation are equivalent. They both have the same solution set. Okay? And this idea of equivalence, is what we kind of strive for when we do these these algebraic manipulations. We try to do these manipulations so that we're always from one step to the next creating an equivalent equation. When we're working with these radical equations, so it's a radical equation because my variable is under this square root, what we do to eliminate that square root is we actually will be squaring both sides. Okay? And that's kind of, what we say that we do. Mathematically, what we're really doing is not that. But for convenience and for, ease of use for most people, we say we can eliminate this square root by squaring both sides. Okay? So if we do square both sides of this equation to solve, what we end up with is x squared equals, and we say that the square root of 2x plus 48 squared, we say that the square cancels out that square root, giving us 2x plus 48. Okay? So when we square both sides, what we end up with is a root-free equation. Okay? But when we square both sides, we don't necessarily create an equivalent equation because we don't have that squaring property of equality. So the solutions to this may not necessarily be the solutions to this, but if our original equation does have solutions, we'll find them in the solution set to this equation here. And so now we can go through and solve that equation. Now we've got a quadratic equation, so we can solve using, at this point, the only method that we would know for solving a quadratic equation is the factoring method. Okay, so if we want to solve by the factoring method, we want to get our equation equal to 0 first. So I'm going to subtract the 2x and the 48 from both sides of our equation. So we'll have x squared minus 2x minus 48 equals 0. And now that we have it equal to 0, we can try to factor to solve. So this is probably some review for you as well. When we're trying to factor a trinomial, 3 terms, what we're trying to do is rewrite it as the product of 2 binomials. Okay? So it would have to be, when you're working with this, that these 2 expressions multiply to the first term. So this first term times this first term needs to give us that first term there. So to get x squared, I can multiply x by x. Also, when I multiply these 2 numbers, I should get this term here. So this number times this number, last times last, should give us the last. And so you can think about all different combinations of numbers that you can multiply to get 48. You can multiply 1 by 48, you can multiply 2 by 24, you can multiply 3 by 16, 4 by 12, or 6 by 8. Okay, and those are all the different combinations of numbers that multiply to be 48. Not only do they have to multiply not just to 48, but to negative 48. And so the only way I can multiply and get a negative product is if I multiply a positive number by a negative number. So I know that one of these has to be positive and one of these has to be negative in order to multiply a positive by a negative to get a negative 48. Okay? And for this all to work out, so we have this times this has to be the x squared. This times this has to be the negative 48. And when I do my inner plus outer, that has to equal the middle term, which is negative 2x. So let's say we try, an 8 here and a 6 here. I know that I'm going to get my negative 48 when I multiply. When I multiply these 2, my inner 2 together, I get 8x. When I multiply my outer 2 together, I get negative 6x. And 8x and negative 6x, that does not add to what I need it to add to. 8 and negative 6 adds to positive 2, and I need it to add to negative 2. So in this case, it's just a quick, easy fix. Because I see that if the 8's positive and the 6 is, if the 8's negative and the 6 is positive, then that sum would end up being negative 2x. So all I'm going to do is switch my 2 signs. So I'm going to make this negative and I'm going to make this positive so that this is negative, this is positive. That is negative. So now I have a negative 8x plus 6x, and that does give me negative 2. So now we have the factorization. And the idea behind this is, the reason we do the factoring is because now we say this guy times this guy equals 0. And from what we know about multiplication, the only time you can multiply and get a product of 0 is if you multiply by 0. So the solutions would be any number that makes either of these factors equal 0. So looking at this, if x equals 8, this factor equals 0, and this product would then be 0. If x equals negative 6, negative 6 plus 6, this factor would be 0, which would make this product equal 0. So our solutions to our root-free equation are 8 or negative 6. Okay? But remember, the solutions to your non-radical equation may not necessarily be solutions to the original. And anything that isn't any solution here that's really not a solution to this, we call those extraneous solutions. Okay, so we always have to check. And if you go back to, what you know about square roots, I'm going to, let me erase my squaring. You don't need to erase yours. I just want to not have that in here while I'm giving you this explanation. But really what's going on, now that we've been talking about square roots, we know that this notation for square root, this signifies what we would multiply twice to get this. This statement, this equation says this is the number I'm going to multiply 2 times to get this expression here. And so when we square both sides, you can see that's really what we're trying to demonstrate, right? This says if I multiply this equation says that x is the number that I multiply twice to get 2x plus 48. So logically, if I multiply x twice, I should get 2x plus 48, right? So that's what's going on here. But I failed to say one very important word, and and this is something that we talked about when we first started talking about square roots. Let me write this down up here just as a demonstration. If I ask you to find the square root of 9, you're going to tell me that the square root of 9 is 3, right? What do I multiply twice to get 9? That number is 3. But we know we can also multiply -3 twice and get 9 as well. This notation, it doesn't just say what do I multiply twice to get 9. It says what positive number do I multiply twice to get 9. The positive number I multiply twice to get 9 is 3. Okay, so when we have that square root there on our paper, it's not just any number that we multiply twice to get it. It's specifically the positive number that we would multiply twice to get this. And so if you look at this up here, if you substitute 8 back in, this says 8 is the positive number I multiply twice to get 2 times 8 plus 48. When you check it, 2 times 8 is 64. I'm sorry, 2 times 8 is 16. 16 plus 48 is 64. And the square root of 64 is 8. Right? We get this true statement. We have 8 is the positive root of 64, right? And that is true, which means 8 is a solution. If we substitute -6 in, 2 times -6 is -12. -12 plus 48 is 36. And so we have -6 equals the square root of 36. That statement is false. Remember, the square root of 36 is the positive or the principal root of 36. The positive number that I multiply twice to get 36 is not 6. -6, I'm sorry. -6 does not equal the principal root of 36. This is not a true statement. So -6 is an extraneous solution. Okay? So the problem that we run into is sometimes we get both numbers that will give us positive roots and also negative roots, but we only want the principal roots, and so that's why we're checking for these extraneous solutions. So 8 is the only solution to this equation. Next example, so we've got x equals the square root of 49 minus 8x plus 7. And so for us to be able to really work through this and understand that statement of truth, just like we were doing before with solving absolute value equations, we always wanted to isolate the absolute value so that we could think about that truth about the number inside. Same thing here. We want to isolate the square root so that we have this statement that some number is the square root of 49 minus 8x. Okay, so always, 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 big star here. Before you do any of your squaring, you always want to make sure that you're isolating your square root first. So we're going to subtract 7 from both sides of our equation. That makes the square root all by itself on the right-hand side, which is our goal. So our equation now is x minus 7 equals the square root of 49 minus 8x. Okay? And so what this says is the square root of 49 minus 8x says the positive number that I multiply twice to get this is this, right? So it should be, if I multiply this twice, that I'll get my 49 minus 8x. Or we say if we square both sides, let me do that in red. So if we square both sides of our equation, we have, so on the left-hand side, I'm squaring x minus 7. I'm squaring that binomial. So I have x minus 7 times x minus 7 equals 49 minus 8x. Okay? So now I have this equation that I need to solve. I have this root-free equation, and we need to solve using the appropriate method. How we solve if there's an x squared involved is different than how we solve if there is not. Solving a linear equation, we just work to isolate the variable. Solving a quadratic equation, we're going to have to factor. But first we need to go ahead and get everything simplified. So on the left-hand side, we need to FOIL. X times x, we have x squared. Negative 7x minus 7x, that's minus 14x. And negative 7 times negative 7 is positive 49. Okay? After FOILing, I see that I have this x squared. So this is a quadratic equation. And if we have an x squared, then we will solve by factoring. Okay, that's the only method we know right now. In the next chapter, we're going to learn some more methods, but right now, we should know how to solve by factoring. So taking our equation, x squared minus 14x plus 49 equals 49 minus 8x. If I want to be able to solve by factoring, I'm going to have to get 0 on one side first. So I'm going to subtract the 49. And because I did it on the right-hand side, I'll also do it on the left. I'm going to add 8x, same thing, on both sides. So now I have 0 on the right-hand side. On the left-hand side, I've got x squared minus 6x, and that's plus 0. Okay, so I've got x squared minus 6x equals 0. Let's write this so it's a little bit more condensed, not so spread out looking. Okay, so we've got x squared minus 6x equals 0. And so on the last example, when we got to this stage, we had a trinomial that we needed to factor. In this example, we only have two terms, which is, we call that a binomial. So anytime I ask you, anytime that you need to factor a binomial, it's only special binomials that are factorable. Binomials that are special are those that have a GCF, those that are a difference of squares, a difference of cubes, or a sum of cubes. So anytime you have a binomial, the first thing you should always look for is a greatest common factor. X squared and 6x, both of these terms have a factor of x, so that is a greatest common factor. So to factor this, I will factor out the x, and so that would be x times x minus 6 equals 0. Okay? The reason for factoring, again, is so that you have a product. We have this times this equals 0. And the truth that we know is that the only way we can multiply and get 0 as a product, right? The only way we can multiply and get 0 as a product is if we multiply by 0. So our solutions are the numbers that would make either factor equal 0. So if x equals 0, then we'll have 0 times negative 6, which is 0. And also if x equals 6, then this is 6 minus 6, that's 0, and 6 times 0 is 0. So the solutions to our root-free equation are 0 and 6. Okay? But again, remember, we have to check for extraneous solutions, any values that really don't work. And like I was saying before, those are related to those, ending up really with negative roots. But if you check it, you can always go back to the beginning. So 49 minus 8 times 0. This 8 times 0 is 0. 49 minus 0 is 49. So what we have when we substitute 0 in to the original equation, we have 0 equals the square root of 49 plus 7. Does it work? Is that true? The square root of 49 is 7, and 7 plus 7 is 14. 0 equals 14 is a false statement, which means that 0 is an extraneous solution. This does not work. And you can really see why it doesn't work if you look at really right here where we've isolated the radical. Okay? Because if you substitute 0 in for x, you have 0 minus 7 on the left-hand side, which is negative 7. And 49 minus 0 equals the square root of 49. So what happens is that gives us really the negative root, right? Negative 7 equals the positive root of 49. That's a false statement, right? Checking with 6 as well. So if I can check in the isolated portion, I do, because it's a little bit easier to see. The 6 minus 7, that's going to give you negative 1. 49 minus 8 times 6 is 48. That gives you positive 1. And negative 1 equals the square root of 1. That's false as well. Okay? But always, if that's not making sense to you, you can always check it back in the original. If you substitute 6 back into the beginning, this original equation, you get 6 equals 49 minus 8 times 6 is 48. 49 minus 48 is 1. So we end up having the square root of 1 plus 7. And again, that's false. And because it's false, it doesn't work in the original. It is an extraneous solution. So we see that both of the solutions that we found were extraneous solutions. So what that means is that this equation has no solutions. Okay? Or we can say that the solution set is empty. Both are acceptable. For f of x equals the square root of x minus 8 plus 7, find all values of x for which f of x is equal to 13. Okay, so to solve this equation, so we want to find values for which f of x equals 13. So we are going to take our 13 and we're going to substitute it in for this f of x. And we have 13 equals the square root of x minus 8 plus 7. So now we have this square root equation, this radical equation that we want to solve. And our method is always isolate your root first. So we're going to subtract 7 from both sides. So we've got 6 equals the square root of x minus 8. And this is just a reminder, make sure that you only square both sides after you have isolated. If you square before, you're not using a truth, right? Once we have it isolated, it says 6 is what we multiply twice to get this. So when we're squaring, what we're doing is we're taking 6 and multiplying it twice to get the radicand underneath. Okay? So adding 8 to both sides, we have 44 is equal to x. Checking that in our equation, 44 minus 8 is 36. The square root of 36 is 6, and 6 plus 7 is 13. So it works. Or checking it here, and where you've isolated the radical, you see 6 is the positive root of 36. That is a true statement. So 44 is the value of x for which f of x equals 13. If I substitute 44 into this function, if I input 44 into the function, the corresponding output is 13. And that's what I'm looking for when it asks me to do all of that. Okay, some more notation. We've got x equals the quantity 2x plus 9 to the 1/2 power minus 5. Okay, when you're seeing this, when you see fractional exponents, fractional exponents are alternative notation for radical expressions. It is true for any integers m and n with n positive, or I'm sorry, with n greater than 1, we define a to the m over n as the nth root of a to the m power, or the nth root of a all to the m power. So when you have these fractional exponents, so something to the 1/2 power, if we use this, so a to the 1/2 power then would be, the denominator is the index, the numerator is the power of the radicand. So that would be the square root of a to the first, which is simply the square root of a. So anytime you see something to the 1/2 power, that's the same thing as the square root. Okay? So working with this, and if you want, it's okay, you can rewrite this as the square root of. It's not necessary to do so. I'll show you something else. So if we add 5 to both sides, we have x plus 5 equals 2x plus 9 to the 1/2 power. Okay, or x plus 5 equals the square root of 2x plus 9. And so what we know, what we've been talking about, is that if we do have these square roots, we can get rid of that square root by squaring both sides. And what you see, I'm not even going to rewrite it as a square root. I'm just going to leave it, and I am going to square both sides right now. If you go back to what you learned way back when, was that if you have an exponential expression raised to another power, then to simplify, when you've got an exponential expression raised to a power, you multiply those two powers together. So 2x plus 9 to the 1/2 squared, I can simplify by multiplying those exponents together. If I multiply 2 by 1/2, I get 1. So squaring, when it's to the 1/2 power, basically gives you just the 2x plus 9. So we have x plus 5 squared, so times x plus 5 equals 2x plus 9. Now we can go ahead and square. On the left-hand side, we'll get x squared plus 10x plus 25 equals 2x plus 9. We have an x squared in our equation, so we're going to solve using the factoring method. So we're going to get 0 on one side. So we've got x squared plus 8x plus 16 equals 0. We've got a trinomial, so we're going to factor that into the product of two binomials. So first times first equals the first, so x and x. Last times last has to give us positive 16. So if this is positive, the only way I can get a positive product is if I multiply two positive numbers together or two negative numbers together. Because I want the sum of my inner and outer to add to a positive 8, I know I'm going to use two positives rather than two negatives. Okay, if it had been minus 8, I would have needed to use two negatives instead. And so I can multiply 1 by 16, 2 by 8, or 4 by 4. But if I use either of these combinations, when I do inner and outer, I'm not going to get a sum of 8 in the middle. So I want to use the 4 and the 4, plus 4 plus 4, because then inner plus outer does give me my middle term. So x squared plus 8x plus 16, the factorization is x plus 4 times x plus 4. And for this to be true, at least one of these factors has to be 0. So if I let x be negative 4, then negative 4 plus 4 is 0. And actually that's 0 too. And the product is 0. So in this case, the only solution to our root-free equation is going to be negative 4. If you factor and the two factors are the same, then you're only going to have one solution. Checking. If you substitute negative 4 in for x, so we've got negative 4 equals 2 times negative 4 is negative 8. Negative 8 plus 9 is 1. So we have 1 to the 1/2 power minus 5. So 1 to the 1/2 power, that's the same as the square root of 1. Here, I'm going to move this up a little. Maybe move out a little. So if we've got 1 to the 1/2 power, that's the same thing as the square root of 1. The square root of 1 minus 5 does give me negative 4. So negative 4 is a solution to this equation. Okay? One more example, and this one, this kind of gives some people a little bit of troubles at times. We have the square root of x plus 4 equals the square root of x minus 1 plus 1. So in this equation, we have a radical equation with a square root on both sides. If there was no plus 1 here, this would be actually very easy to solve. Okay? If there was no plus 1, I'm trying to just cover it up. If I squared both sides of the equation right now, I would get rid of both of those square roots. With the plus 1, that complicates issues. Okay? So this says that what I multiply twice to get x plus 4 is this whole thing. Okay? So to solve this equation, I have to multiply this whole thing twice to get my x plus 4. So when I square both sides, I have x plus 4 equals the square root of x minus 1 plus 1 times the square root of x minus 1 plus 1. Okay? So we have to actually multiply those two binomials together before and simplify and go through a whole bunch of junk. So with that extra plus 1 and then the two square roots, we're actually going to have to square a couple of times in order to get rid of all of my radicals. So we have x plus 4 equals, so if I multiply the square root of x minus 1 by the square root of x minus 1, I'm getting the square root of x minus 1 squared, right? And so we should see that what I multiply twice to get x minus 1 squared is x minus 1. So the square root of x minus 1 times the square root of x minus 1 is simply x minus 1. Square root of x minus 1 times 1, we've got plus the square root of x minus 1. 1 times the square root of x minus 1 is plus the square root of x minus 1, and 1 times 1 is plus 1. Okay, on the right hand side I have like terms that I can combine. Negative 1 plus 1, and when you're working with radicals, remember, if they have exactly the same radical part, you can add them together. So we have x plus 4 equals, leaving my x, negative 1 plus 1 is 0, and 1 root x plus 1 plus 1 root x plus 1. When you are adding like terms, remember you add the coefficients and you leave the radical part the same. So 1 plus 1 is 2. So we've got plus 2 root x minus 1. And so now, before we can solve for x, we're going to have to get rid of this square root. And as we've discussed, if we want to eliminate the square root, we're going to square both sides. But before we square, we need to isolate. So to get the square root by itself, I need to get rid of this term. So I'm going to subtract x from the right-hand side. And then to maintain equality, I'm going to subtract it from the left as well. So I have now 4 equals 2 root x minus 1. I'm going to show you two different approaches that you can take, because in your homework you're going to see sometimes that this second approach is necessary. So I really have two approaches to solving that I can take right now. So first option, second option. Okay, option 1 for solving this equation as it stands right now. To truly isolate this square root, we would need to get rid of that times 2. And to get rid of that times 2, I would divide both sides by 2. So I have 4 divided by 2 is 2. Those cancel, so I have the square root of x minus 1. And now that I've isolated that square root, I can square both sides to solve. So square both sides. 2 squared is 4. And On the right hand side, the square root of x minus 1 squared is just x minus 1. So what I have now is an equation without an x squared, just a linear equation. So I'm going to isolate the variable, add 1, and I get x equals 5. Okay? Since we are solving a radical equation, we do need to make sure we check that 5 really works. So if we do, we get 5 in the original equation, 5 plus 4 is 9, and the square root of 9 is 3. So we get 3 on the left-hand side. 5 minus 1 is 4. The square root of 4 is 2, and 2 plus 1 is also 3. So if we substitute 5 back into the original equation, it does make a true statement, so that guarantees that 5 is a solution. This second option that I'm going to show you is an option that you're really going to need if you're solving these radical equations and you get to a point, let's say, you're solving some other radical equation and you get something like 5x plus 3 equals 7 root x plus 2. Okay? So if you're solving and you have something like this, and we try to use this first option, which is to divide both sides by 7, then you're going to have this major mess on your hand, because those 5 and 3, those numbers are not divisible by 7. So you'd have this 5 sevenths x plus 3 sevenths equals the square root of x plus 2. And so then you'd have to square both sides, and you'd have to deal with this whole mess of fractions. So to avoid that, which most people want to avoid, dealing with all of those fractions, what you can do instead is what I'm going to show you with this second option. Okay? So typically I reserve this second option for instances. So I would say use this option if the terms on the left-hand side, LHS, left-hand side, are not divisible by the coefficient of the root. Like I just showed you with that other situation. Right? The 5 and the 3 were not divisible by the 7. So if we have 4 equals 2 root x minus 1, we can go ahead and just square both sides of the equation right now. When the only thing that's keeping our square root from being by itself is some, coefficient out front, some multiplication, it is okay to go ahead and square. When we square, remember we're multiplying that thing twice. So squaring 4 gives us 16. If we multiply this thing twice, I'm going to write it up here. We've got 2 root x minus 1 times 2 root x minus 1. But you have to remember that 2 root x minus 1 really means 2 times root x minus 1, right? And then you have to remember, well, multiplication is both commutative and associative. So this is the same with the commutativity. If you're multiplying, a bunch of things together, the order that you multiply doesn't matter. So we can switch these two factors around. So that's the same thing as 2 times 2 times the square root of x minus 1 times the square root of x minus 1. And then we have the associativity property, which says, well, we can group those factors. So we can multiply these two together, and we can multiply these two together. So if I multiply 2 by 2, I get 4. If I multiply the square root of x minus 1 by the square root of x minus 1, I get x minus 1. But don't forget that we're still doing a multiplication. And if you're multiplying a monomial by a binomial, you have to show that using parentheses. So when you square 2 root x minus 1, you end up getting 4 times the quantity x minus 1. Okay? So you just have to make sure that when you do square, when you've got this coefficient, that you not only square your square root, but you need to square your coefficient as well. And you cannot lose sight of the fact that it is a multiplication. You have to say 4 times this quantity x minus 1. So now simplifying this equation, I would distribute my 4. So I've got 16 equals 4x minus 4. Now it's just a linear equation, no x squared, so I'm going to isolate my variable, add 4 to both sides. I've got 20 equals 4x, and then dividing both sides by 4, we get the same solution of 5. Okay, so regardless of the method, you should get the same solution. Okay, 5 is the solution to that equation. So I do this. If every term on the left-hand side is divisible by this coefficient, I go ahead and divide everything by that. If it's not, then I would go with this second option. Let me know if you have any questions. Good luck.